Hello, welcome to an Ozen Engineering video. In this video, I'm going to be talking about Ansys Icepak and more so concentrating on how to model fans. In Icepak, there's a fairly easy way to model 3D fans using the available fan object. However, the fan object sometimes produces behavior that is slightly different than a real fan. And this is due to the flow features like swirl and centrifugal spread due to the spinning of the fan rotor. If you have a CAD model of the fan and the blades, it may be better to resolve the fan and the blade details and use a moving reference frame MRF approach in Ansys Icepak. So for this purpose, I've brought in a CAD model where we have the nice model of our fan. The pink line is the casing of our fan. The red lines indicate the hub and the blades of our fan. And then in blue behind we had that cutout region, which is a transition from the fan volume to the enclosure volume. So far I've kind of hidden other features of this model, and I'm going to start working on my fan model. So in order to do an MRF type approach, what we need to define is a fluid volume. Right now we don't have the fluid volume around the blades. Therefore, I'm just gonna produce a block around our fan. So let's go ahead, double click on our block. Let's name it MRF1. Its geometry is going to be cylinder, and then we're gonna work on the YZ plane, and our center is going to be at this location. I'm just gonna put these numbers in, and you'll see that the geometry will fit in very nicely around our fan. So it will be 20 millimeters high with a radius of 34 millimeters. Let's hit update, and as you can see, our block object covers just a little bit around the blades that as desired, radially and also axially. So that looks good. Let's also assign this block a rotation of 6,000 RPM. And then let's click done. Well, obviously, also have to change it to fluid. So now we turn on the MRF option. And then let's name it MRF1. Hit update and done. Now that we have our MRF domain for one of the fans, we want to replicate it for the second one. So we can easily just go do a copy, and we're going to make one copy of it, and we're going to translate it in the Z direction. And let's see, we're going to translate it minus 74 millimeters. Let's hit apply. And as you can see, again, we have a nice fluid volume around our geometry. So, and let's just, rename this MRF2. And then what we want to do is move these over here so that they have lower meshing priority, because what we want is for the fan objects to have the higher meshing priority. As you know, in Icepak, the objects that are lower in this tree will have higher priority. So, and we can check it. So let's double click. This has a priority of 38, and we want something smaller, so 36. So that's exactly what we wanted. Now let's make the rest of the domain visible. And what we can see is we have these multiple assemblies within our domain where some heat is generated. We have our fans and the two grills or openings in the min and max X directions to pull the flow through. Next step is going to be meshing. So we're going to go ahead and click the mesh button up top here, this one. And then I'm going to set these maximum element size, that were determined beforehand for a quick and efficient mesh. Let's make the gap 1 millimeters. Course, we want to mesh the assembly separately, and then we also want to use set uniform mesh parameters. This will come in handy for our fan mesh, and use average. So let's put this aside for now. One thing we want to do is we have our fan objects. These are the solids. We don't want to really resolve the solids, so instead of solids, we can just turn them to hollow to save on meshing, and then I'm just going to click done. So we need to do some careful high quality meshing for our fan region. So let's double click on our assembly. Let's go under meshing. And then we want to mesh this zone separately. And again, I'm going to put in some slack settings that are appropriate for this particular geometry. These will be our slack settings. And we don't want to use global mesh control settings. We want to set our own maximum element sizes and gaps. So that the mesh is really fine-tuned. Again, we want to check on set uniform mesh parameters. The next critical step is we want to use multi-level settings. So these will help us capture fine details without adding lots and lots of cells. So we want to allow multi-level meshing, and then keep the proximity and curvature size functions on, and let's click edit levels. So this is going to bring up component by component levels that we can specify for multi-level meshing. So higher the level, it's going to do a finer level of mesh. It's going to, each time it's going to halve the hex mesh. So I'd like to change some maximum levels. And one thing I find is if you go click here and try to punch in a number, it does not work. So what you want to do is actually go here and double click the left mouse button, not single click. And let's start putting some numbers. Again, Don't forget to double click, and so we'll do one, and then on the blade surface we want to do 3 layers of meshing, multi-level meshing, and I'm gonna hit accept. And we're done with the setting up the mesh. So let's hit done. Go back to our mesh control window. We already made the changes here, and then as a recap, we went under the fan region where we defined certain settings, particularly multi-level meshing, to capture the fan geometry accurately. So let's hit generate, and it's going to start the meshing, and then what we want to do is examine the mesh. After about a minute, our window came back. Now it says a number of elements around 383,000, which seems reasonable, and which tells us, it was able to generate a mesh without any problem. But let's, look at our mesh. So let's go to the display tab, turn on display mesh. So right now it shows the mesh on a cut plane, but in this particular case I'm more interested on the fan surface. So I'm gonna click on surface. Let's pick this and let's say wire. Click on selected object. Because I had selected the fan, it's only going to show the fan object. So now we can zoom in to our object and we can see we're properly resolving the geometry. So that's pretty good. Maybe we also wanna look at a section. So I'm gonna add a cut plane, and then I'm gonna pick the Z-axis and maybe move it a little so that the plane is somewhere cuts through our fan, and then we can kind of see the mesh here. If I essentially hide all these components, it's gonna look a little better. Let's do that. Then let's go select our fan object. So now we can see the detailed mesh in the fan region and the rest of the enclosure. Of course, we go click the quality button, we see that we have good face alignment, and then let's see, and skewness is also acceptable. So I'm going to hit close. Now that the mesh is ready, we essentially want to go and set up our model. So let's go. Let's say basic parameters. We want to solve for flow, temperature, radiation. We don't care at this time. We want to use the realizable 2 equation turbulence model, which is more appropriate for rotating frames, because right now we have our blade, there is swirl that is being modeled and captured, so we want a proper turbulence model, which is realizable 2 equation model for this case. Because it's forced convection, we don't need to turn on natural convection option. Next step is doing some basic settings for numerical solution. As this is a complex flow, let's just put in 1000 iterations. Also tighten the flow convergence criteria by 2 orders of magnitude. For turbulence, we don't need this level of accuracy, and let's hit accept. So before submitting any job, it's always best to put some monitor points. we want to make sure the solution is converged. So for example, I want to put a monitor point near the fan, right? I want to look at the velocity, pressure, etc. So what I'm going to do is I'm going to go to the points. I want to hit create that point, and here as you notice I have the mesh still visible, and near this fan region what I'd like to do is select the option nearest, go near points, maybe click and and as you can see I placed a monitor point in this region. I can look at velocity here, and I hit accept. So we can add as many monitor points as we like at different locations, but for this model I'm just gonna stick with this single monitor. So let's hit close, and then we're ready to execute our model. So we go to the run solution, and then it's going to be a new start, and then let's hit the start solution button. So once the solution is available, we'd like to take a look at the temperature field, for example. So let's do object face. Let's pick our objects. Let's select everything, maybe except the fan assembly. Let's hit accept. Look at contours of temperature. So after some clearing up, we can see the heat generating components, and what we see is temperatures may be as high as 59 degrees C, where particularly hottest are where the heat is generated the most. So that does make sense. Another way to look at the solutions is, let's deactivate this, add a cut plane. Let's make it Z plane, and let's look at flow speed, and select this object, hit apply. So we can see that there's a fast flow region there. Let's cut through roughly the center of the fan. Let's take a look at the flow speed solution, and maybe limit the flow speed to maybe 5 meters per second. So this is actually what it looks like, for the flow domain. And what I'd like to do is essentially just, make a copy of this picture for comparison. In the next step, what we're going to do is switch to the 3D fan object, turn off our MRF approach, and then switch to the 3D fan solution and compare the results. See, what are the differences between the more detailed MRF approach versus the simplified 3D fan approach. And in Icepak, that's very easy. Let's, for example, just close this, and what we'd like to do is we want to inactivate the fan model and the components, and look at the, and then we're gonna just activate the 3D fan model, which is this pink block here. So let's go ahead and look at this object. So this is our 3D fan object. If we expand on it, what we essentially have are this simplified version of the fans, and with their power curve, fan curve, and with their similar dimensions. So now we have activated this and inactivated the MRF model. So all we have to change is maybe just change the convergence criteria flow to 4 orders of magnitude. That's it. We can just now submit the run. Let's give this a different ID. Let's call this fan object, and then just start the solution. So it's doing remeshing, and then it's going to submit the job and execute the model. So now it looks like we have a converged solution. We're gonna hit done, and then we're gonna look at the same view, and this is what the model predicts using the 3D fan model. And here, you know, I'm showing the results at the bottom on the same color scale, same view, when we've explicitly modeled the blade and the you know, rotating swirling zone. As you can see, you know, the flow distribution is fairly different, particularly near the fan area. So, you know, this suggests us that whenever possible, we should be using CAD models along with the moving reference frame approach with Icepak as well as other CFD models. That concludes our presentation for today. Thanks for your patience. Have a good day. Bye.